All right. Before we begin today's lecture on vectors, I want to take a little walk down memory lane. First of all, on a map, north, east, south, west, just a little reminder. And also from geometry, if we have two lines or line segments that are running east and west, and they're cut by what we call a transversal, another line or line segment intersects both of them, then the alternate interior angles are congruent to one another. Okay, so this angle would be congruent to that angle. They'd have the same measure. This angle would be congruent to this angle. If you have two parallel lines that are running north and south, and they are intersected by a line or a line segment, it would be called a transversal in geometry. Again, the alternate interior angles are going to be congruent. For instance, if this is 60, that's 60. If this were 120, this would be 120 degrees. Okay? So just something to bear in mind as we begin working with vectors. Here we go. Let's see if I can find the actual lecture now. There we go. Trig lecture 412 through 415. We'll be doing this for 4 days next week. Just have a couple of problems a day. The student will use vectors to solve problems involving force and velocity. Well, let's see what a vector is. A vector is a directed line segment. When you draw it, it's going to look a lot like a ray. It's going to be a line segment with an arrow on one end. But unlike a ray, it's got a finite length. A directed line segment has two characteristics. A vector has two characteristics, direction and magnitude. In the magnitude, you can think of the magnitude as just the length of the line segment. Okay, and the little arrowhead is the direction of whatever force we're going to be talking about, or velocity. We will be adding vectors today and next week using the tip-to-tail method. And hopefully I will make that clear here in just a second. The sum, that means we're going to be adding, of two vectors is called the resultant. So if you're asked to find the resultant, it means add the vectors together. And here's how you would do it graphically using the tip-to-tail method. Example, add the following vectors. Find the resultant of the vectors is another way of saying that. So if you have this vector, it's a line segment indicating a force moving in this direction or a velocity, and a line segment indicating a force or a velocity moving in that direction, and you were asked to add them together, you would just use tip to tail. Tip is the pointy part, tail is where the force starts. So you're going to take the tip of this one, put the tail of that one on it, if I can get it on there, and then the resultant vector would be from here to here. There's our resultant. Okay? And you don't have to add them I didn't have to start with this one. I could have started with this one and added this one to it. Oops, I lost my arrow. And I would get the exact same resultant. Okay? So it doesn't matter which one you start with. That's adding vectors in a nutshell. Tip to tail. The tip is the pointy part. Put the tail of one on the tip of the other. The direction of a vector can be communicated in a lot of ways. We'll be determining the direction as follows. And here we go, I'm going to give some examples. Sketch a vector with a given direction and magnitude. Now I want to sketch a north 30 degrees west direction, magnitude of 500 miles per hour in this case. So here's what I would do. I'll say, well, here's north, south, east, and west. And a lot of people do this with a dotted, but it's too hard to dot for me. Now I'm going to go north 30 degrees west. Move this down a little bit since I'm going north. North is like in this direction, and I'm going to put the tail of my vector here and then leave it here and rotate from the origin 30 degrees to the west. Okay? Whoops. Get that out of there. So here's what I'm going to do. Rotating 30 degrees west, we go whoop, about like that. Here's about 30 degrees. Now I'll call this 500. In this case, miles per hour. And that's how I would sketch that particular vector. It looks kind of curved, but that's all right. It's just a rough sketch. Okay, north 30 degrees west. This angle would be 30 degrees. This one's south, 40 degrees west. So since I'm going to go south, I'll say, well, here's where my vector is going to start. I'm going to move in a southerly direction and rotate 40 degrees west. So that would be about like this. Rotating 40 degrees west would give me something like that, and I would call this 2,000 newtons. That's the length of my vector. Newton is a measure of, or a unit of force. Capital N is the is what we use for newtons. Okay, so there it is. South 40 degrees west. This is south 40 degrees west. Let's take a look at another one. North 70 degrees east. So again, we start like this. I'm going to rotate to the east this time. I'm going to rotate 70 degrees, so that's going to be more like this. Rotating almost 90 degrees. There's my rotation of 70 degrees. And I'm going to call that 200 pounds, just because it tells me to. Okay, so there's 200 pounds in a direction north 70 degrees east. This is 200 pounds. So 100 pounds will be half of that once I've established what 200 pounds is. And here's another one we're asked to do. South 38 degrees east. So I'll start up here. There's north and south, east and west. And I'm going to go south and rotate 38 degrees east. So that'd be something like this. The 38 degrees that we rotated is right there. And our direction of rotation was like that. And 600 kilograms, so I will call this 600 in this particular case. So a 1,200 kilogram vector would be twice as long as this. Once I establish that this is 600, we base everything else off of that, the lengths of them. So that's a quick introduction on how to graph them, graph vectors, tip to tail. I'm sorry, to how to sketch them with a given direction and a magnitude. We haven't put them tip to tail yet, but we're about to. Sketch the sum of indicated vectors tip to tail. Okay, so I've got a vector that we're going to call vector V. Notice that I'm going to blow this up real quick. That symbol looks like almost like a ray, but it's not. It doesn't have the little arrow point there. Okay, so that's vector V. So I'm going to add these together. Here we go. I'm going to go south 20 degrees east. South 20 degrees east. And I'm going to call that 30 newtons. And I'm going to call this 20 degrees right in here because I rotated 20 degrees. And then from here, I'm going to have another little north-south thing going on there. You think of it as the origin. And we're going to put the tail of this vector right here. And I'm going to go south 80 degrees, south 80 degrees east. So I'm going to go south 80 degrees east. So that's almost that way. And this would be a 10 degree. This little angle right here would be 10 degrees. And so if I know that this is 20 degrees, and this is parallel to this, then this alternate interior angle right here has got to be 20 degrees too. I might need that at some point. But there we go. We've added them together. And does it say find the result? Nope, we just sketch them, sketch the sum. I'll go ahead and find the result anyway. I'll make it blue. From here to here would be the resultant of those two vectors. Okay? Let's see if we got another one to do. Nope, we're just going to do a word problem. So that's basically what we're going to be doing with word problems. And notice we get a triangle. Tip to tail, resultant is a triangle. We have the law of sines and the law of cosines to use as tools. So that's what we're going to do. Let's take a look at this problem right here. The plane leaves an airport traveling north 40 degrees east at 200 miles an hour. The wind is blowing at south 60 degrees east at 50 miles an hour. Find the resultant velocity. The velocity is the speed of the airplane that's being affected by the wind. So it was going 200, but the wind's going to affect it. And the direction. Well, it was going north 40 degrees east, but the wind going in this direction is going to affect the direction of the airplane. So here's how we would do that using vectors. I'm going to go north 40 degrees east, so I'll start down here. I don't need arrows on that. That's just north-south right there. East-west. And I'm going to go north and rotate 40 degrees east and call that 200 miles per hour. And here's the direction that I'm moving. It's a vector. And then I'm going to add the wind. I'm going to add the wind, and I'm going to add it tip to tail. The wind is blowing. I'm going to put the tail of the wind right here on the tip of the airplane velocity. So I'm going to graph it right here. The wind is blowing south, 60 degrees east. So it's going to be about like this. I'm going to rotate 60 degrees. And that's going 50. So if this is 200, 50 is a little shorter than that probably. This doesn't have to be perfectly to scale, but something we can work with there. Now let's take a look at what we did. We rotated 40 degrees east. So this is 40 degrees. Right there, it's hard to read. This angle right here is 40 degrees down here. That rotation. And therefore, since these lines are running north and south, this angle is also 40 degrees. Right there. That's 40 degrees also. North-south, north-south. They're parallel, alternate interior angles. Now I just rotated this angle south 60 degrees east, so I know that this angle is 60 degrees. That's a 60-degree angle right there. And that makes this angle 40 plus 60, which is 100. So I'm going to move those out and write 100 right here. This is a 100-degree angle. That's very helpful. This thing represents 50 miles an hour. I'm almost ready to solve this puppy. So I went north 40 degrees east, and then south 60 degrees east. And now I want to find the resultant. So I'm going to go from here. Okay, I think I'll use this tool here. Make it a little straighter. This is what I'm looking for. I'll call that the resultant. And now, find the resultant velocity. That's the length of this line segment. And the direction of the plane. Well, the direction of the plane is going to be north. So many degrees east, it's going to be more than 40. It's going to be this little angle right here added to 40. And we'll call it theta, or alpha. The length of this is 200. My direction of my resultant is going to be moving from the north. I'm going to rotate 40 plus alpha. So when I go to state my direction, I got to remember that it's going to be north 40 plus alpha. This is just a little reminder. You don't have to write this. Degrees east. And I'm going to find the resultant just using the law of cosines, I think. Because I'm looking for this, I'm given this, this, and this angle, which I figured out. And here we go. R squared. In fact, here's what I'm going to do so I don't cover up my drawing for you. I'm going to move my drawing to where you can kind of keep an eye on it while I'm working. There we go. Here we go. I want to find my resultant first. I'm going to say r squared is equal to 200 squared plus 50 squared minus 2 times 200 times 50 cosine 100 degrees. That will give me the length of this resultant using the law of cosines. And so now I'm just going to try to put this into my calculator and get an approximation for the length of this segment which will give me the speed of the airplane. If I haven't made any mistakes, let's see if I have 200 squared plus 50 squared minus 2 times 200 times 50 cosine 100 equals, that gives me the square of the velocity, so I want to take the square root, gives me the square of it, and that is 214.4. I'm going to round to the nearest tenth. And that would be whatever our unit of measure is. I think it's miles per hour. Yes. So this would be 214 miles an hour. So the wind is affecting us. The plane was going 200 miles an hour, but the wind is moving it to where its vector is a little bit longer. Now the wind is, the speed of the plane is 214.4 miles an hour, right? That's one of the things we were asked for. Now I want to find the direction. Well, the direction I'm going to rotate 40 degrees plus whatever this angle is. And I can use the law of sines now. I got this for 214.4 miles per hour. And I can say, well, 214.4 is to the sine of 100, as 50 is to the sine of alpha. And once I find alpha, I add it to 40, and that'll give me my direction. So here we go. 50 over sine alpha is equal to 214, this is an approximation, over the sine of 100. Hopefully I haven't made any mistakes. I'm going to cross multiply 50 sine 100 is equal to 214.4 sine alpha. So that will give me, dividing both sides by 214.4, we'll solve it for sine alpha. And to find alpha, we take the inverse sine of both sides. I'm not going to bother writing that, I'm just going to do it. I'm going to enter this into my calculator and take the inverse sine of it. Hopefully I won't mess it up. But here we go, 500 sine 100, I'm going to say equals, divided by 214 equals, and I'm going to take the inverse sine of that. 500 sine 100 equals, divided by 214.4 equals, I have messed up something. Oh, that's 50. I'll put 500, that's my problem. Oops. I said 50 is to the sine of, not 500. Sorry about that. All right, let's try it again. It shouldn't be, I should have, when I multiplied sine 100 times 50, I wrote 500 because I'm an old man and my brain's dying. Here we go, 50 sine 100 divided by 214.4 equals, and we'll take the inverse sine of that, and that is 13.3-ish. 13.3 degrees is alpha. So the direction I'm moving is 40 plus 13.3. I'm going to rotate 40 degrees and then another 13.3 due to the wind. So my direction is north 53.3 degrees, east. That'll be the direction I'm moving. And my speed or my velocity will be whatever it was I just found. What did I just find? 214? Those are the two things we were asked for. So if I was in a multiple choice situation, I'd look for both of those. And hopefully those are right. I've got the answer key around here somewhere. 214.4 miles per hour at north 53.3 degrees east. Yay! Alrighty, hopefully I've made it clear that our vectors are added tip to tail. Your resultant will form a triangle, and you have the law of sines and the law of cosines at your disposal. And don't forget, alternate interior angles are congruent, and you can use that to find angles like this one. If this was 40, that's 40. We rotated 60 degrees, making this angle 100 degrees. And then I had a triangle. I knew everything I needed to use the law of cosines. You can do this, ask me questions in class, or Zoom.